Welcome to this lecture on impedance control of robot manipulators. As we have seen, impedance control is one of the two main type of control design that is being pursued in order to handle the interaction between the robot, in particular the robot and the effector, and the environment with which this end effector is in contact. It is best suited for a situation in which the environment undergoes small, although finite, deformation at the contact. So this design is not suited for a situation where we know in advance that the environment is very stiff. We will analyze the design of such a control law, which essentially goes through a sequence of two steps. The first step is a feedback realization control. The second step is the assignment of a desired behavior, which is made through a suitable chosen reference model, which is accepted called the impedance model. We will see the various application and variants that can be realized, and then we will make some simplification that reduces the general scheme to a more simplified one. So, impedance control imposes, in fact, a dynamic interaction between the robot and the effector and the environment. We are not explicitly controlling the contact force, we are not explicitly controlling the motion at the contact, but in fact, we choose a reference model which relates forces and displacement at the contact. This reference model is chosen as a generalized system made of a mass, spring, and damper in each direction of the Cartesian space. The choice of the parameters in this impedance model is made accordingly to some desired characteristic of the transient and of the contact force that should be set under control. These systems are typically linear, but also nonlinear version of such reference model can be considered. In this context, we are not modeling explicitly the way in which reaction forces are being generated by the environment in response to a small deformation. So we are not assuming that the environment behaves like a linear spring or simple model as that. We don't require this. In fact, for some stability analysis, we will make some assumption of this kind. Because of the uncertainty which is typically associated with a compliant environment, both in position, orientation, and in the compliance characteristics, there is no way of regulating contact force using impedance control. So the main objective is to limit the amplitude of the contact force. In fact, we will see that there are cases in which we are also allowed not to measure the force at the contact. So since we are not measuring in some situation this contact force, we cannot even regulate that value, closing a force feedback loop. So since there is no force error loop in this scheme, the contact force are resulting from the motion that we are imposing through the dynamic impedance scheme. And in particular, when we choose some parameters in the dynamic impedance, in particular, we specify a specific stiffness in the spring of the impedance model. This results in a trade-off between how accurate we would like to achieve a position with respect to how large the contact forces are allowed to arise. So the setting is the usual one. So we have our Lagrangian model on the left hand side of the model of the equation. On the right hand side we have the generalized forces produced by the actuators and new forces, which are the forces arising to the contact. There's a Jacobian transpose which in general associates the forces and momentum at the contact to the equivalent joint torques. Now a consideration should be made at this stage. We have seen that we can model a robot which is constrained to a given geometric surface at the end effector level, for instance. In that case, on the right hand side, we have seen that the Jacobian of the constraint appears. Now, this is instead the Jacobian of the robot. It could be the geometric Jacobian of the robot, or, as we will see in a moment, also the analytic Jacobian. So what is the difference between these two models? In one case, the forces that arise, in fact they are qualified as Lagrange multiplier lambda, appear on the right hand side pre-multiplied by the transpose of the Jacobian associated to the constraint, which means that we can only consider forces applied, for instance, at the end effector, which are generated by the attempt to violate this constraint. So, for instance, the direction in which these forces are being exerted are related to the geometry of the environment. In this model, instead, we assume that forces may be applied in any forces and momentum, so generalized forces, may be applied at the end effector by the environment in any direction. So there is more freedom associated to this. We are not really constraining the end effector to belong to a geometric surface. So with this in mind, we have the generalized Cartesian force added on the right hand side of the dynamic model. We assume that there are n joint coordinates in this dynamic model, and we make the following, give the following definition, and we remember also a number of relations. So the force may contain, the generalized force F may contain linear forces and torques, gamma and mu, in a number which is m, with m less or equal than 6 in case. So if we are considering the full set of generalized forces, so 3 forces and 3 torques, m will be equal to 6. Otherwise it could be even less. Now these forces are performing work on generalized velocity. So if we take the 6-dimensional case, we would have a generalized velocity which is composed by a linear velocity v, a 3-dimensional vector, and the angular velocity omega. And indeed, this 6-dimensional generalized velocity is connected to the joint velocity q dot by the geometric Jacobian. Now we remember that while the linear velocity is the time derivative of the position of the end effector in this case, the angular velocity omega is a vector which is not equal to the derivative of a minimal representation of orientation, for instance, using Euler angles. So there is a difference between omega and phi dot. While p dot, which is equal to v, and phi dot can be obtained with analytic differentiation of the direct kinematics from the joint space to these quantities p and phi. So this analytic Jacobian will be defined here as JA times q dot. Now there is indeed a relationship between the geometric Jacobian that we use in the first equation of the dynamic model on the right hand side and the analytic Jacobian, which for this presentation will be preferred for a number of reasons. So we know that the Jacobian, the analytic Jacobian, can be obtained through the product of a matrix which is related to the particular set of angles that we are using for representing the orientation, so a matrix TA of phi to the geometric Jacobian. we have also defined singularity of the robot structure as the singularity of the geometric Jacobian. The analytic Jacobian has additional singularity, which are those of the minimal representation of the minimal representation of the orientation. Okay, so with this in mind, we can also substitute to the right-hand side of our equation, instead of using the geometric Jacobian, we can use the analytic Jacobian. The dimensions are the same when we are dealing with this type of representation, but indeed we will have on the right hand side not the forces and torques acting on the end effector, but in fact a modification of these quantities, which is related to the principle of virtual work. So we will have generalized forces that perform work not on capital V, but on x dot. One or the other can be used. I prefer to use the analytic Jacobian in the following, and we will comment why this is more convenient and more practical in a sense. So remember also that we have developed a dynamic model in Cartesian coordinates. So if we rewrite the full model in the presence of a contact in Cartesian coordinate, and from now on we will assume that the number of joints is equal to the number of coordinates in the Cartesian space, in particular the number of generalized forces that can act on the system, so that the analytic Jacobian is square, then the full model in Cartesian coordinate can be rewritten in this mixed form. You see that the argument of the vector Gx of the matrix Sx and of the inertia matrix in the Cartesian space M of x are still function of Q and Q dot, because we typically model the system in the joint space and make the transformation to deal with Cartesian quantities. So in fact, the Cartesian inertia matrix is obtained from the joint space inertia matrix by premultiplication by the inverse transpose of the analytic Jacobian and post-multiplication by the inverse Jacobian. And similarly for the other terms. And we know that there are some usual structural properties holding, so that the Cartesian inertia of the robot is positive definite as long as, I would say, if and only if the Jacobian is non-singular, the analytic Jacobian is non-singular. Also, the Cartesian inertia and the factorization of the Collier-Ritz and centrifugal form of terms in the Cartesian space satisfy the skew-symmetric properties, so m dot minus 2sx is skew-symmetric, and the full model can be linearly parameterized in terms of a set of dynamic coefficients. We will not use the latter properties, but the previous one is important. Why we refer to the dynamic model in the Cartesian coordinate? Simply because now on the right hand side, the forces that the generalized forces that act on the end effector appears directly without any matrix multiplying them. And because the problem of interacting with the environment is in fact a problem well defined in the Cartesian space. So we start with this model for designing our control law, and then when we end up with the final expression of the control, we try to simplify terms and see what can be rewritten in terms of joint space quantities. So the design of an impedance control law is based on two steps. The first step is feedback linearization in Cartesian space, which we have already done, but now we will consider the presence of a force and, in general, of a force measure. So we assume for the time being that we have a force sensor mounted on the end effector, which is capable of measuring any contact force applied beyond the force torque sensor. Now, feedback linearization is very simple if we look at the Cartesian model. So we just cancel the Cartesian dynamic terms of gravity, gx, the Cartesian term related to velocity, so sx times x dot, and we introduce a new signal a, which is an acceleration in the Cartesian space, pre-multiplied by the inertia, by the Cartesian inertia. In addition, we eliminate any force that we may measure at the contact. All this has the dimension of a Cartesian generalized force, so in order to apply the torque at the joint level where the motors are present, we pre-multiply this by the Jacobian transpose. The result is that the acceleration at the Cartesian level is equal to the new signal A. So we have obtained a closed-loop system at this stage, which is made by double integrator between the new inputs and each component of the Cartesian acceleration, despite of the presence of a contact force, because we have removed it by control. Indeed, we cannot really expect to let now the end effector accelerate in any direction freely unless we tolerate forces that becomes incredibly large when we are trying to enter into a compliant but at some point resisting environment. So some completion of this control law should be made in the choice of A. And this is in fact what happens when we specify, when we impose an impedance model, which is our reference behavior. In this model, there are several terms. So the model prescribes the way in which external forces coming from the environment, the one that we have measured and subtracted in the feedback linearization control law, interact with a reference trajectory specified at the end effector level in terms of a position, xt, its velocity, xt dot, and its acceleration, and the actual position, velocity, acceleration of the end effector, pre-multiplied this variation of behavior by an apparent desired inertia, a desired damping, and a desired stiffness. So these are positive definite or semi-definite in case of the damping matrices, which are typically chosen as diagonal. So this specifies for each direction, generalized direction in the Cartesian space, the way in which we would like the robot to interact with the environment. As you can see, there is no information on how external forces are coming. The only thing that we are saying is that we are measuring them with a force torque sensor. Now, there are many things to have to specify in this general structure, namely how do we choose the element on the diagonal of the tree matrix, and why are we choosing them in a particular way, how to define a reference trajectory when we are in contact or in the vicinity of the surface of the environment, and so on. So, but we'll leave this on the side for a moment and make a choice of the auxiliary input A in order to match this model. How do we do this? Simply we replace to x double dot in the impedance model that we have chosen the value A, and then we solve for A. If we do this, what happens is that we assign to A the following expression: the desired acceleration plus some gain, which is the resultant between the inverse of the apparent inertia that we are imposing times the desired damping and the velocity error. Same story with a desired stiffness times the position error, plus again the measured force. So the force appeared twice, once in the feedback linearization control and the other in the choice of the desired acceleration of the acceleration input A in order to match the impedance model. Now, one thing that we immediately specify is how to choose the desired motion. Now, when we would like to keep contact, because the main intention here is to keep contact and move in contact while keeping contact forces limited. But the main addressed issue here is that we would like to keep contact, and the environment is a bit compliant. So it's kind of natural to choose the desired motion, the reference motion, that we will not be able to replicate because of the presence of the environment, slightly inside the compliant environment. So this will induce some contact forces, and these contact forces will help to keep the end effector in contact with the environment surface. So let's do some example of how, qualitative example of how the desired reference can be chosen in impedance and also later on in compliance control, which is a subclass of this impedance scheme. So this is the model. For instance, when the robot is doing a grinding task. Now, this task suppose that the involved component, the robot, the tool, and the surface are relatively stiff. Still, we can impose some compliant behavior by the choice of an impedance model. In this case, we have a contact point. Let's denote this x of e, and we have a desired trajectory while the robot is doing the grinding, so while it's moving the tool in contact with the metallic surface, which moves a little bit beyond the surface. So there will be some error, and this will be counteracted by the forces that arises due to the contact. And the way in which these reaction forces from the environment to the end effector of the robot interact with the motion of the end effector is specified by the impedance model. This is another schematic example in which we have a surface which is supposed to be compliant and also not linear. So we have a curved surface. The robot is mounting a tool. In between we have also a force torque sensor, and the tip of the tool should follow a path on the surface of this environment. But in fact, the reference trajectory is designed according to the surface itself, but a little bit inside the geometric surface. Indeed, the end effector will not be able to reach the desired trajectory, so we will live with this position error, but associated to this position error, because of the imposed impedance model, we will have also some contact forces implied, and these contact forces will guarantee that the end effector keeps continuous contact with the environment. And by the choice of the parameter in the impedance model, we will also make sure that this force is not too large if we have tuned well the parameters. Another example is the following one, in which we consider a constant desired pose. So the trajectory vanishes into a constant xd, so x double dot desired and x dot desired goes to 0. And for instance, this is the situation in which an impedance model can be assigned to the interaction between the end effector of the robot and a human operator moving around the end effector. So the force now is being applied in an autonomous way. We don't know where and how, in which direction, and what will be the intensity, by a human operator that is carrying around the end effector. The desired configuration is the one at this contact, and you can see that when the human is moving the end effector in different direction, it will generate an error with respect to the reference value xd, and in response to this, the robot will generate the contact forces according to the impedance model. So if we make the system very stiff in one direction, then the human will feel the need of a high force in order to have the same amount of displacement. If we, in another direction, the stiffness will be the desired stiffness, so in the impedance model will be low, then it will be very easy to displace the end effector from the reference position xd by the human. So the human will have to apply less force, and so on. Indeed, increasing the inertia, the apparent inertia, will let the human feel a very heavy robot end effector to be moved, and vice versa. If we reduce the apparent inertia, the feeling will be to move a very light object, the feeling from the human operator side. And the same is in case of collaboration, so it's not manual guidance by the human robot, by the human operator. And this picture, which is taken from a video of a collaborative task that we implemented on a lightweight robot, KUKA lightweight robot in our laboratory, a human is applying the force, and the system is being programmed with an impedance at the contact point. The contact point in this case may not be the end effector, it could be any point along the structure, and we use a specific model-based method in order to estimate the contact force and then possibly to regulate this contact force even without the use of a sensor. So this goes into a separate chapter of our program, collaboration in human-robot interaction task, but we can implement an impedance method also in this case, with the extra characteristic that we are doing this at any contact point, not necessarily at the end effector level, which is the standard way in which impedance control is being designed. Okay, so when we move the contact point from the reference constant position, we will induce this type of impedance behavior. Now, with this in mind, so having chosen a model and having chosen a reference position or a trajectory slightly inside the surface with which the robot end effector needs to be in contact, we substitute the acceleration A into the feedback linearizing control. We get rid of all the Cartesian terms, we rewrite them in terms of the original model terms, so the inertia in the joint space, the factorization of the Coriolis and centrifugal term in the joint space, the gravity in the joint space, and we see that there are additional terms. In the first line of this expression, we have after the inertia matrix and the inverse of the analytic Jacobian, so that we are assuming that this Jacobian is squared. We have the desired acceleration coming from the impedance model. We have a term that is related to the curvature of the Jacobian, so J dot Q dot. And then we have a PD-like term coming again from the parameter of the model, cancellation of gravity and of Coriolis and centrifugal term, and in addition, pre-multiplied by the transpose, pay attention, only by the transpose in the second row of the control law, the second line of the control law, pre-multiplied by the Jacobian transpose, we have a special product, the Cartesian inertia of the robot, multiplied by the inverse of the desired or apparent inertia, minus the identity, multiplied by the measured contact force. So this matrix is weighting the measured contact force. In general, if this is the situation, we will need to measure contact force. So we will need to carry a force torque sensor on the end effector for implementing impedance control. But we will see that we can also simplify these terms. In particular, if we look at this last term in the control law, while the other terms, apart from those coming from the impedance model, are all written in joint space term, we can rewrite also this term by remembering the expression of the Cartesian inertia matrix, and in fact in this identity we end up with a control law which is all expressed in joint coordinates. Remember that we design the behavior and we cancel the dynamic term in the Cartesian space, so using the Cartesian dynamic model and using an impedance model which is defined in the Cartesian space, but eventually we need to impose a joint torque at the joint level, and it's convenient to use all dynamic terms expressed in terms of the generalized coordinate q and their derivative q dot. So this is the full picture. Now this is in fact what I've just commented on the implementation of the control law. Now we turn our interest on the choice of the impedance model. So what is the idea behind? First of all, as I said, there is no regulation of contact forces. We would like to avoid impact forces when we enter in contact and large reaction forces when we keep contact. And this large impact and large forces may be due to the uncertain geometric characteristic of the environment. So geometric in the sense of where we enter into contact with the environment and how is the environment oriented with respect to the end effector of the robot. This is one aspect. The other aspect is that we would like to adapt the robot behavior to the dynamic characteristic of the environment. So, stated in a simple way, we would like to have a complementarity. The more stiff is the environment, the more soft should be the behavior of the robot, and the controller should achieve this target. On the other hand, the more stiff, the more soft is the environment, the stiffer can be the robot in pursuing its desired trajectory. In the limit, in the direction where the environment is so soft that there is no environment at all, so there is free motion, we could be infinitely stiff. Complementary, in the direction where we expect to encounter a very stiff environment, the controller will comply completely. So will not attempt to reach the zero desired position, but will let the force, the contact force, remain low by reducing its own stiffness. And all these aspects are realized by the proper choice of the apparent inertia of the desired stiffness and as a consequence of the desired damping in the impedance model. And in fact, we can also have a bio-inspired choice by looking at how we move our arm in the presence of uncertain geometry, which tends to be fast and stiff when we move our arm in free motion, but when we expect some contact, so we are proceeding with a guarded motion, we will be slower and more compliant. Okay? And by slower and fast we associate essentially the equivalent mass that we like to move. By stiff and compliant, we associate the desired stiffness in the various directions. So, those Cartesian directions where we expect to have a contact, we will choose a large apparent inertia component, m of m I is the generalized component. Let's consider for the time being only linear direction, So in a direction where we expect to hit a wall, we will use a large inertia in the prescribed closed-loop behavior, which means that the system will reduce its acceleration and speed. And at the same time, we will use a small desired stiffness, because when we will enter into contact, this will let the robot comply in a more clear way with respect to the environment. So this will generate low contact forces. On the other hand, in the direction where we expect the motion to be free, we will do exactly the reverse. So we will have a small apparent inertia so that we can accelerate very quickly, and a large stiffness gain so that we will follow a desired trajectory which has this component free to move. We will follow it with good tracking properties. Now, once we have chosen these two quantities in every Cartesian direction, we will complete the choice by selecting the damping coefficient, which on a second order system will guarantee, for instance, no overshooting or a smooth transient behavior without oscillation. So the damping coefficient is typically chosen at the end of the process, considering a second order mechanical system like this. Now, indeed, this is one aspect, so low contact forces and good tracking, low contact forces in the direction where we expect contact, and good tracking in the free direction. And this choice, as I anticipated in my introductory part, I suggest that we should know something about the geometry of the environment. We cannot be completely blind to it, because otherwise, if we expect in a direction that one direction is completely free for moving the end effector, while instead there's a hard wall in that direction, the choice of a bad impedance model will be a disaster in terms of performance. So, as I said, there's another aspect that is a generalization of what we have just said. And here I'm using the bio-inspired analogy. So suppose that you are in your room at home, but your senses are not perfectly well tuned. Probably you are moving in the dark, so you know where to expect. For instance, you want to switch on the light with the switch on the wall. So you're moving your hand toward the wall, and you expect in one direction that you may hit the wall before you expect. The wall is very hard, so you have a guarded soft motion in that direction. So you move slowly and you're ready to comply with any contact. On the other hand, looking for the switch on the wall, so moving right and left, where you don't expect any contact, then you will be relatively fast and relatively stiff in order to execute your command. So you see that this type of behavior is well fitted to the expected uncertainty, but indeed, if your senses are completely off, you may expect that the wall is in a different direction. For instance, if you're coming late home at night, a bit drunk, then your senses will certainly not be in perfect shape, although you have an idea of the geometry of your apartment, and then some disaster may happen in the sense that you may hit and damage your hand while moving in this situation. So you see that there's another aspect. If the wall would be there with its geometry, but be soft, in fact, we don't need to be so soft from the side of the motion contact. So there is a complementarity. The harder we expect the environment, the softer we are. And the slower we move. In the limit, fully hard environment, very slow motion, very compliant, so low desired stiffness in that direction. In the other direction, soft, expected soft environment, or even no environment at all, which is the softest possible environment that we can think of, very low inertia, very fast speed, and very high stiffness, very large accuracy in prompt reproduction of a reference trajectory which is moving in the free direction. So this is the idea behind, and it's a very successful idea. In fact, this idea was introduced by Neville Hogan, who developed both the biomechanics and bio-inspired concept and then its robotic application. Okay, so this is the basic design. Now there are some simplifications that we can introduce. The first simplification essentially concerns the choice of an apparent inertia, which is not different from the natural Cartesian inertia at the contact, so at the end effector level. In all this presentation we assume that the contact occurs at this level. So we don't change this apparent inertia, which means that in our model, instead of using a diagonal constant desired inertia m of m, we will keep the Cartesian inertia m of x of q. So we are giving away the possibility of letting the system behave faster or slower by choosing the appropriate apparent inertia. So we preserve the natural Cartesian inertia. So we are giving away some nice feature of the impedance model, but we win a very big advantage, namely in the matrix premultiplying the measured force in the control law, there was a factor m of x times m to the minus 1, m of m to the minus 1, minus the identity. And if we choose the apparent inertia exactly as the Cartesian one, the first term is an identity subtracted to another identity, and the measured force will vanish from the control law. So we can achieve this modified impedance model, which is now a non-linear impedance model, because the inertia that we are imposing is a nonlinear function of the configuration of the robot. It's not a constant matrix. In this control law, we will not use the contact force feedback, so we don't use a force torque sensor. So this is a very common implementation of impedance control law, exactly for this reason. Now, if we look at this control law, force has disappeared, and we see that apart from cancellation of nonlinearity, gravity, and Coriolis term, the rest of the control law is in fact has a PD structure with some feed-forward acceleration. So it's a pure motion control law in the Cartesian space. The only specific aspect is that the parameters of the proportional and derivative term, so Km and dm, now the inertia has been chosen as the natural one of the robot in the Cartesian space, so the only parameter left are Km and dm, and these are chosen in such a way that we expect limited counterforces in the direction where we anticipate contact, and good tracking in the direction where we expect the environment to let the end effector free to move. Okay, so there is a, let's say, an interpretation of the standard PD gain in terms of what we expect in the interaction with the environment. Now there's a an additional technical issue, which is not clear in the beginning. If we are choosing an impedance model which has a configuration-dependent inertia matrix, namely the Cartesian inertia matrix of the robot, then if this should correspond to a real mechanical system, mass spring, damper, or a generalization, a nonlinear generalization of this, then we know that associated to a non-constant inertia, there should be also Coriolis and centrifugal term, which are not present in an impedance model which has m of x of q as desired inertia, namely the real inertia of the robot at the end effector level, while the remaining part of the model contains just a constant stiffness and a constant damper. So this would not represent a real mechanical system. And as a consequence, some convergent properties of control laws that uses, for instance, the conservation of energy, so some physical properties that allows to conclude about the stability of some control law would be lost when we are imposing this type of behavior. Something strange may happen, or possibly may not happen, but we cannot exclude that something strange will happen. So, if we want to be accurate, and this is another type of simplification that we introduce, we should include a fully nonlinear impedance model, which, beside the actual Cartesian inertia, m of x, includes also a term which carries over the factorization of the Coriolis and centrifugal terms, so the matrix S of x, which will multiply a velocity term in the Cartesian space, in fact a velocity error term. So only the gravity has disappeared from the picture. Now, if we redo the computation by assigning, so by doing feedback linearization first, so this is a conceptual scheme. We do feedback linearization because we eliminate what is inconvenient in a sense, and we are left with a double integrator commanded by the signal A. Now the signal A, or x double dot equal A, the new signal is chosen in such a way that we match the impedance model, in this case the nonlinear impedance model. We choose A in this way, and then we introduce this in the original feedback linearization controller, and we see what happens. And what happens, the final control is the one that is shown in the blue box, which is slightly more complex than before because we have included in the desired behavior even the Coriolis and centrifugal term, but has a few advantages. First of all, again, there is no need of measuring contact force, so of using the Forster sensor in the impedance scheme, because we are using the actual Cartesian inertia in the impedance model. And second, when there is no contact situation, so this is a conventional tracking controller with a time-varying x desired of t, so we can guarantee using Lyapunov argument and the presence of this q-symmetric term m dot of x minus 2s of x into the derivative of the Lyapunov candidate, that we will get zero tracking error. So we have seen this before. We cancel gravity, and you can see that there are all terms that appear linearly are computed with the desired value of the Cartesian trajectory. And in fact, we will also have further simplification when the reference motion included in the impedance model degenerate into a constant. So if xd is in fact constant. In fact, in this case, if we replace xd dot equals 0 and x double dot equals 0 in the previous expression, we end up with a well-known controller. In fact, this is a Cartesian PD control with gravity cancellation. We have already studied this control law in the absence of contact. Remember that the fact that the control law does not include a measurement of the contact forces, it does not mean that there are no contact forces at all. But we know that in this case, when regulation is chosen as the desired trajectory in the impedance model, remember that we are simplifying the general impedance control law by making a number of modification to the impedance model and to the reference motion, which is now constant. So when we have no contact, we already know that this control law achieves global asymptotic stability of the desired position xt, provided that the Jacobian has full rank. We have seen this in the Cartesian control analysis that we have already made. And indeed, since we are now moving to the situation when we are transiting from a non-contact, so free motion situation to a contact situation, we should understand what happens in that case. We expect that we will not get asymptotic stability of the desired xt because xt is not even an equilibrium. In order to understand what happened, we can redo the same proof of the Cartesian PD control law with gravity cancellation by slightly modifying the Lyapunov candidate. In fact, we are using we can use as candidate the Cartesian kinetic energy of the robot and an elastic term which uses the stiffness of the impedance model Km. If we do the computation and we do the substitution, we end up with a derivative of the Lyapunov candidate, which is negative semi-definite, and from there on we can conclude using LaSalle asymptotic stability of x of t if the contact force is absent, so if Fa is equal to 0. What happens when we have contact? And we are not using the contact force in our controller, which is now, it's an impedance controller that degenerates to a much simpler one when we used also nonlinear terms in the impedance model, and the reference motion in the impedance model is constant, so xd is a constant. So for understanding what happens, only for the analysis, so far we have not mentioned how contact forces are being generated from the environment and will appear in the model. We have only measured them if we would like to change the apparent inertia, and we don't need even to measure them if we use an impedance model with the Cartesian inertia of the robot instead. So for analysis now we assume that we have an elastic contact model. So we will have forces generated by the fact that we are entering inside the environment is placed in this formulation in a position xe, and we have a stiffness through which the environment is reacting to small deformation. Now this stiffness matrix Ke may not be strictly positive definite because in some direction we don't have any contact force arising. In some other direction the value of Ke is certainly positive. So where we are really in the direction where we are really entering the environment. So we use this expression for Fa, and in order to understand what happened with the closed-loop system, we modify the previous Lyapunov candidate by taking the same candidate as in the free motion, but adding some other energy term, potential energy term, which is associated to the deformation of the environment. And this will be a quadratic term in the deformation with the matrix K of E inside this term. So the new Lyapunov candidate V2 will be V1 plus this term. Now, one should look at where this Lyapunov function now has its minimum, and if this minimum is 0, it will not be in the desired configuration xt, but it will also not be in the contact position xe, where the end effector of the robot enters in contact with the environment. There will be a different minimum for this Lyapunov function. We will get, we'll explain where it is in a moment. But if we take the time derivative, we end up again with a semi-definite negative function, and using again Lassalle, we can conclude about stability of the equilibrium point, the point where the Lyapunov candidate has its minimum. And in fact, if we look at the closed loop system at the equilibrium, we will realize that all the velocity and all the acceleration are gone, the gravity has been compensated, so what remains is just the balance between the stiffness of the controller, which is km times xd minus x, so with respect to the desired position, and the stiffness of the environment, which has been modeled as a force that is proportional through the gain ke to the deformation xe minus x. So the equilibrium at this point will be unique, because you can solve this equation for x, and you will find a value of x which we label as x capital E, which is exactly a form which is a combination of the desired position and the point of contact xe in which the robot enters in contact with the environment. Now, this xe will be, in fact, exactly the minimum of the Lyapunov candidate V2. So our previous analysis showed that this minimum, this particular position, is the equilibrium and is the asymptotically stable equilibrium of the robot in contact with such environment under the action of a modified impedance controller. So Lassalle concludes that this is the asymptotically stable equilibrium. Now, if you look at the expression of x capital E, pay attention. Now I would like not to confuse the capital E, which stands for equilibrium, to the small e as subscript, which stands for environment. Unfortunately, I'm abusing terminology, but it is quite clear, if you look at this expression, that this equilibrium, when the environment is sufficiently rigid, more rigid than how stiff is your controller, so when Ke is much larger than Km, then this equilibrium will be close to the surface of the environment, which means that we will not deform the environment because not too much, because large deformation will be associated with very large contact force. So this is something that we want always to avoid within an impedance scheme. On the other side, if the environment is much softer than the controller, so the controller is the rigid one, so Km is much larger than Ke, from the above expression of the equilibrium x capital E, subcapital E, we will see that this position will be close to the desired value xt. So we are getting quite at the desired destination by deforming the environment, provided that the rigid controller is sufficiently stiff. Of course, if the environment is stiff and we make the controller even more stiffer, then, although it's true that the equilibrium will be close to the destination xd, the resulting force that can be computed will be very large. Anyway, so there's a good choice would be, again, not to try to overcome a stiff environment with an even stiffer controller by the choice of Km. So this type of control law, so compensation of cancellation of gravity plus PD control with the gain chosen according to the expected stiffness of the environment, is also called in the literature compliance control. which is a sub-case, as we have seen, of an impedance control when the reference trajectory in the impedance model is constant, when we have chosen as apparent inertia the actual Cartesian inertia of the end effector, and when the Km has been chosen in the model, has been chosen depending on the expected stiffness Ke of the environment. We're getting slowly to an end. Now, there's another simplification that we can perform. Supposing that gravity is compensated or cancelled mechanically, supposing also that there's no damping term, and supposing that the deformation, so the difference between the actual desired position and the desired position and the actual position is small, then we can approximate this variation in Cartesian position with a variation in the joint space multiplied by the Jacobian. Like we do for velocity, we do for this transformation with small displacement. So the Jacobian is there anyway. So the control law, it becomes simply the following one. The dm term is gone to 0. We have a J transpose in front, and we have Km times xd minus x, which is replaced by Jacobians times Kd minus Q, which simply shows that if we are imposing a constant stiffness in the Cartesian space, through the equivalence J transpose times Km times J as a new configuration-dependent stiffness in the joint space, we are saying that the constant stiffness in the Cartesian space is equivalent to a configuration-dependent stiffness applied to small errors between the current configuration and the desired one associated with the Cartesian value xd. So this type of understanding shows that what we are doing is the active equivalence of an RCC device. So we are reacting by the choice of a diagonal Km to forces with small displacement in the direction of the applied force, because we have chosen a constant and diagonal Cartesian level stiffness. This is associated to the fact that in the joint space, the actual displacement is multiplied by a stiffness matrix, which is configuration dependent instead. Now, there's a nice way of considering this type of mapping if we look at the relation between stiffness and transformation of forces. So, as we said, a compliant controller, or a stiffness controller in this case, react with forces to displacement. So we have assigned in this case to small displacement dx, which is the variation with respect to desired position xd at the Cartesian level, the generation of a force which is proportional through Km to this type of displacement. In this sense, this is exactly the opposite of what happens with an RCC device, which generates a displacement in reaction to a force. But the mapping is one-to-one because Km is diagonal, so in every direction we have this type of behavior. This is what we call, in fact, stiffness control. With this in mind, however, we know that this dx may be computed through the previous formula as the Jacobian times a small variation in the joint space. And similarly, that the force at the Cartesian level through the Jacobian transpose becomes a torque at the joint level. So if we go around this way, which is exactly what the formula is saying before, so U is JA transpose F, and F is Km dx, and dx is JA dq, so U is J transpose Km J times dq. So if we go around this circle, this is equivalent of having a configuration-dependent stiffness at the joint level, which associates to a variation of position, delta Q, with respect to the desired reference, a torque in reaction as a control. Now, the same is true when we reverse the order. When we are having some constant definition of the joint space, what happens then at the Cartesian level? However, this inverse relation, so the vice versa, applies, but not working with stiffnesses, but with their inverses, so with their compliance. So suppose that we have a torque applied at the joint level, and this induces a joint displacement. And we can choose this compliance Cm as a diagonal matrix. So every torque generates an associated displacement at the joint level and not at the other joints. So if we start, this is exactly in blue, is exactly what we started from in red in the other diagram. And now we move this joint torque in the Cartesian space. We assume that the system is square, so that we have a square Jacobian. So if joint torques are coming from forces pre-multiplied by JA transpose, Cartesian forces are coming from joint torques by the inverse of the Jacobian transpose. And similarly, this type of law can be realized, the delta Q is associated to delta X through the inverse of the Jacobian matrix. And now if we do the round in this way, and we would like to complete the cycle, so going from U to delta Q without going directly in the joint space, then we have to associate a compliance, so a relation between a force and the displacement now. So a force generates the displacement in the Cartesian space through a C of x, which is position dependent. So the relation now goes from U to delta Q, and when we impose a Cm constant and diagonal in the joint space, we are in fact imposing a configuration dependent compliance in the Cartesian space, going the counterclockwise rotation in this diagram. Okay, so this was the active counterpart of the remote center of compliance. So this is in fact a stiffness control, which is seen as a subcase of the impedance control in the general setting, having made a number of choices of simplification of regulation task inside the impedance scheme. I would like to conclude now with another way of looking at things. So far we have always considered as the input command to a robot some torque that the motor should apply. In a control architecture, this torque commanded is typically realized for electrical motors by imposing some current at the motors, because we know that torques are proportional to the current, and knowing the current to torque conversion factor, all our torque level design controller are implemented by imposition of a specific current. If this is not possible, we have a closed control architecture, and in fact we can only command kinematic quantities and rely on a low-level controller. Then what can we do in the presence of interaction with the environment? Then this is the situation in which we use admittance control. And admittance control, as we have said, relates contact forces to velocity commands. Okay? And the implementation, using exactly compliant matrices, as we have seen in the second diagram of the previous slide, can be made either at the velocity or at the incremental position level, and can be realized either at the joint or at the Cartesian and task space. Remember that we end up with some command which is a kinematic command, either a velocity or an incremental position. For instance, if we assume that the relation between a contact force and an associated joint torque is given by the Jacobian transpose, and then we command a velocity q dot, which will be realized by the low-level controller, closed controller of our robot, and this relation will be a function of the commanded torque u. So we will have a C of q, which is a compliant matrix generating the q dot, and if we put these things together, we will see that by choosing a non-negative, typically positive definite compliance matrix in the joint space, the contact force will be transformed into a command in velocity. So if we see a force pushing the end effector, this, and we measure this force, this will move the joints through this relation, C of q, which is a gain matrix, in fact, times the Jacobian transpose. And this is what is called admittance control, which is now designed with a matrix at the level of joint. The same thing could be done if instead of generating directly a velocity command, we generate an incremental position command, which is added to the current q and constitute the new position reference for the low-level control. A similar consideration can be done in terms of Cartesian task. Now we assign a compliance at the Cartesian level, so once we have a contact force, we measure this contact force, we associate a desired compliance at the Cartesian level, so we generate a velocity in response to this contact force by a C of x matrix, again positive semi-definite, because in some direction we would like not to react, so in those directions say x is 0. C of q or C of x are typically chosen as diagonal. And now, once we have generated this x dot, supposing that we have a non-redundant robot, we invert this velocity command and we generate the q dot or the delta q if we wish, as before. So we have j to the minus 1 times the compliance at the Cartesian level in reaction to the Cartesian force f of c. And if the robot is redundant, we just replace j to the minus 1 with the pseudo-inverse, and we realize what is called admittance control, now with an admittance or a compliant matrix, which is defined in terms of the Cartesian or task space. And with this, we complete this type of control for handling the interaction. We have seen many variants. In the next lecture, we will move to the case of hybrid control, where we are controlling explicitly both the force and the motion, typically in the presence of a stiff environment. We will see that we can also complement impedance with hybrid controller when we are dealing with the control of forces in the direction that our hybrid scheme imposes. Thank you for listening.